Hello fellow skeptics, I'm Luther Name, and this is the 10th video in the series on the general topic of is something wrong with modern physics, and if so, what, and can it be fixed? Now, we've been delving into the underpinnings of special relativity, the Lorentz transforms, the Doppler expression, and the aberration. In this video, the 10th one, we're going to begin to discuss in detail the Doppler, places we haven't used it and should have, things relating to the Doppler that we've overlooked, and how the Doppler, in fact, impacts technologies that we've used, mostly in terms of academic technologies, things like particle accelerators. It'll be interesting, but we'll show that the Doppler shows that the particle accelerators simply aren't working as we expect. We've already shown that length contraction, time dilation are misrepresentations of what happened in poorly executed and poorly understood and discussed measurements, mostly the Michelson-Morley experiment. But now we're going to talk a little bit about some other aspects of special relativity. We're going to talk about the way the Doppler and its lack of use has impacted technology, but we're also going to talk about the addition of velocities and to show that that's been totally misrepresented. And what we'll show is that there is no addition of velocities in the sense that it was portrayed in Einstein's 1905 paper and has been supported subsequently in the literature and our textbooks relating to special relativity. And we'll discuss why that's true and how. So this is, to begin with, just going to be a slight review of where we are. In the last video, we showed where the Doppler and the aberration expressions came from. We're just going to be talking about the Doppler expression in this video. So this is the general equation where an object with some velocity v and the beta is v over c is moving at some angle phi with respect to the direction of propagation of radiation. If you look at it as a radar scenario, this is the angle that an moving object would make relative to the direction of propagation of a radar beam. So what we have is, to simplify things without really impacting the discussion at all, this is the general equation, and if the object or the target is moving away from the radar, the angle phi is 0, and this is the expression we have. If the object is moving towards the radar, we have phi equal 180 degrees, and cosine of 180 degrees is a negative number, and so we wind up with this expression. Very simple expressions and well proven. So Einstein is famously developed what is called his composition of velocities, and from that he purported to show that nothing can move faster than the speed of light. So what we need to do is take a look at that, because he derived those straight from the Lorentz transforms in the kinematic part of his 1905 paper, and did not at all use electromagnetic radiation propagation as we've seen as we developed the equations in the last video, using simultaneity to show where the Doppler and the aberration expressions came from. So we can explain what Einstein's scenario was that gave rise to this particular expression. This is his composition of velocities, and it goes something like this. And you'll recognize it from the next slide, where we show a scenario where we're going to actually make a physical measurement using a radar. And a radar is an electromagnetic device, a system, and it works by generating a signal, electromagnetic signal. And so we know from the prior video, that's where the Lorentz transforms are used to find
how the Doppler expression. So that's a very legitimate application of Lorentz transforms. So we're going to use that very same system in order to test out whether or not this in fact translates into an actual measurement scenario. And that's what we're up to here, is to test Einstein's composition of velocity to see whether it's valid. So here's the scenario. Scenario is this: you have a stationary radar. Einstein called a stationary frame. Here you have a moving frame on this aircraft. It's now moving at speed v1 relative to the radar. And here you have an object moving at speed v2 relative to this airplane. Not relative to the stationary radar, but relative to this airplane. So you had a moving object and a moving object relative to a moving object. And that was Einstein's scenario. But that's also what we're going to do. We're going to make measurements and see how a physical measurement by this radar and the results we get compares to the results from Einstein's composition of velocities. Now, to do that, though, we need to understand a little bit about how a radar measures the Doppler shifted frequencies. When an object emits a signal of some sort, the motion of that object imparts a Doppler shift on that moving object. If you look at a radar, though, it has a detection process in it. The first thing is that almost all, if not all, moving airborne radars use the ground as a reference or use something else as a reference. They always know how fast they're moving relative to that reference. If it's the ground, then it's a stationary frame of where the radar is in the scenario we talked about before. The moving radar always knows it's moving. It has to. If it doesn't, then you've got ambiguities and there's other issues associated with it. From the first thought experiment that Einstein put together in his 1905 paper, we also know, when properly evaluated, that we can it's some sort of onboard system to determine how fast that object is also moving. So it's in principle possible for any moving platform to know that it's moving and at what speed. In the case of a radar, an airborne radar, it has references with respect to the ground, or possibly it's getting a reference from that ground-based radar, closing the loop, giving it a feedback in terms of what its speed is. So what that does is it allows certain Doppler shifts to be basically eliminated. That approaching Doppler shift and other Doppler shifts associated with receipt of the radiation scattering off the second object coming back the first time, they can be automatically eliminated. And it's because they use a process called heterodyne and superheterodyne detection. These were common in radio and communication type signals. Ironically, they're very much like these configurations are very much like the configuration of the Michelson interferometer. We have a beam that comes in and is split. That beam, one beam goes at 90 degrees relative to the direction of the propagation of the primary beam. It goes through. It would be like the radar beam being transmitted to some moving object. Scatter radiation comes back. As it in the Michelson interferometer, that radiation that went straight through the mirror bounces off a mirror, comes back, and then the split signal is also bounced off a mirror and comes back, and they're recombined on a detector. This is in principle at a very high level how the detection process also works using microwave or radio waves in something like a radar. And what that does is it allows us to eliminate all these other Dopplers, with the exception and isolate then the one that's associated strictly with the object that we're looking at or trying to detect as the moving object itself. So with that, what we have is that the radar on the moving aircraft will always be able to detect the speed and tell you what the speed is of the second aircraft is relative to the moving aircraft. And we know, of course, that then the stationary radar can do the same thing. And it measures each of those speeds, and it goes ahead and just does a simple calculation to determine what the speeds of all the objects are. There's no special formula. There's no special relationship with these various speeds. It's just simple linear addition. So we have no ambiguities, nor do we have the composition of velocities that's special, like Einstein came up with. Einstein didn't measure any of these velocities. He said, well, this is moving with speed v1, this is moving the speed v2 with respect to the first moving object or frame itself. And again, he basically said, well, it knows that it's moving at speed v2 relative to v1. And so he just said it's true, and he said that we can always know what the speed of the second object is relative to the first object. So in a sense, the scenario is highly contrived. What we can basically say is that the composition of velocities just simply doesn't exist. But the irony here is that, again, there's another issue. You have propagating matter. Quantum mechanics and the Schrödinger wave equation are based on the fact that you, in fact, can have an exponential description of the propagation of an object, of a particle. The interesting thing is that the Schrödinger equation is Lorentz invariant, but the solutions to the Schrödinger equation are not. So you can have, you have then in quantum mechanics the fact that while the Schrödinger equation itself is Lorentz invariant, which is one of the hypotheses that has permeated special relativity, the solutions are not. The electromagnetic wave is, in fact, the solutions are Lorentz invariant, but they're not for a particle. And so, how would you have a solution that's it's not Lorentz invariant in one case, but it is apparently, as Einstein tried to make it, in the case of his composition of velocities? It's just there's this inconsistency that permeates uses of various elements of special relativity itself, not only special but the general theory itself. What we can say is that in general there is no composition of velocities. It's just all simply linear addition of the velocities themselves. There's nothing special about it, and it tends to show that the Lorentz transforms are not legitimate in terms of the application to finite moving objects, directly applicable to being applied to finite moving objects. So it casts into the equation that it basically says that the composition of velocities as Einstein identified it and derived it just simply doesn't exist. So we can go ahead and take a look at it also in an alternate scenario, which is very similar. You have two aircraft approaching one another, two spacecraft or what have you, and they both transmit a signal. And so we know that each one can detect the Doppler shift of the other relative to it, since each one can always know what its own speed is. If it doesn't know what its speed is, well, then you have a different problem. It has nothing to do with the Lorentz transforms. It has to do with information. And one of the things that the French physicist Leon Brion stated as he began looking at the information aspects of building scenarios for various purposes, he indicated that oftentimes Einstein's scenarios just didn't have enough information in them. Well, if you don't have enough information, then you can get all sorts of screwy results or come to screwy conclusions. But in this particular case, as we can see as we look at this, because of the fact that each one of these aircraft knows what its own velocity is, it can always isolate and find directly what the Doppler shift is associated with the other moving object. And so it can take that Doppler shift and add it to its own speed and find out what the closing speed is between the two of them. Again, nothing special, just straightforward. So, but there's some missed physics here that we need to look at in terms of what's happening with the Doppler expression. That has to do with the fact that we know that there's a thing called radiation pressure. And in Einstein's 1905 paper, he showed that there is an impact of the Doppler expression on radiation pressure. And so what we have is, since we have photons, or any flux of radiation can be made up of a whole family of these photons of various frequencies that would be its spectral content. We have that there's the energy associated with electromagnetic radiation, and we can derive that based on the frequency of that radiation. So if we've got a particle accelerator, and the easiest one to visualize would be the one at Stanford University called SLAC, Stanford Linear Accelerator. And what it has is a bunch of microwave klystrons that are beamed down a evacuated tube. It's evacuated to keep the gas molecules from disrupting the beam of electrons. And these klystrons generate radio frequencies, high energy radio frequency, creates a flux that drives the electrons down this tube, a linear tube. And so what you have then is that the flux of radiation is accelerating the particles down the tube. But here's the hook. That if you take a look at electromagnetic radiation, what you find is that as the speed of the object increases, as it's being accelerated faster and faster, the actual radiation pressure that's driving that thing decreases and decreases till it goes to zero. In other words, by the time the thing gets very close to zero, speed of light, there's no force left to push the thing to accelerate it any faster. But it's even so we can never drive something up to the speed of light using electromagnetic radiation because of the Doppler shift. But there's even more than that, and that is that that beam, the tube that is evacuated, it's also sometimes it's cooled, water cooled, can be nitrogen cooled. I don't believe any of them have been liquid helium cooled because all it's used for is to condense molecules of air or whatever gas is in the tube out to keep it from interfering with the beam. If we look at that, what we have though is something called black body radiation. Any object with a temperature above absolute zero has a particular radiation frequency associated with it. Even human beings, any object. If you've used those handheld temperature measurement devices where you measure the forehead of an individual, it's measuring the thermal radiation that's coming off of the individual, and that is related to the temperature of a person or any object, and it has a well-defined characteristic intensity and distribution of frequencies that's in it. That's black body radiation. But it's also true that within those evacuated tubes, that tube has the same temperature as the outside. If it's water cooled, then that's its temperature. And therefore, the inside of that tube is bathed in a flux of radiation defined by the temperature. And when you take an object like an electron and you accelerate it into this black body radiation, it's like a pressure against the movement of the object. In other words, it's a retarding pressure on it. As the faster the object moves into it, the Doppler upshift of that radiation impinging on the moving electron creates a force that counters the driving force. And so what you wind up with is retarding force on the accelerated electron, and therefore it comes to a terminal velocity. It reaches a particular velocity given by the black body radiation in the tube and the Doppler shift of the driving radiation associated with our power that's being generated by the klystrons. There's some 200 of them, I think, in the system. So what you have is that our particle accelerators are simply not accelerating objects to the speeds that we think they are. That our whole understanding of the physics of particle accelerators is incomplete. Coupled with the fact that the kinematics associated with special relativity have now been called into question, I'm not sure what we know about what's happening within these items, within these particle accelerators. So what we have there then is we've got the two effects having to do with Doppler shift that are totally missing from our understanding of the physics of particle accelerators. An actual measurement is made using Doppler expressions. The addition of velocity is just simple addition with no nonlinearities as Einstein's composition of velocities. There is no limitation of the speed of a physical object other than to be able to actually make the object accelerate that fast. For charged particles, we can do it with electromagnetic radiation, but that we don't really know how to do anything other than accelerate charged particles, with the exception of taking high energy single photons like gamma rays and to cause them to strike an electron or an object and for the object to recoil at faster than the speed of light.
So that takes care of the Doppler. This video has been a little longer than I normally would make it because I wanted to get all those particular aspects of the impact of the Doppler and our omissions associated with the Doppler. The next video I'll delve into the aberration, which is the other finding from the electrodynamic part of Einstein's 1905 paper, and as I said before, we can see that a lot of the things that we've attributed to the kinematics of relativity really are the impact of the Doppler, because when we've got light pulses, if we've got accelerated electrons, all those things that require electromagnetic radiation, why we can show that how we perform the experiments or measurements are basically can mimic everything that we've attributed to the relativistic, kinematic relativistic effects. So with that, I'm Luther Name. The next video will be on the aberration, and stay skeptical. If you will or you can, like this video or leave a comment, and till I talk to you in the next video.